Good evening to all.
Good
Uh,
evening, madam.
Good evening, ma'am.
can we start this session, sir? Once again, good evening to one and all present here. On behalf of Dhanlakshmi Srinivasan Engineering College, Department of Computer Science and Engineering is organizing AICT sponsor Atal 6 days online FTP program on quantum computing from 16th December to 21st December 2024. I welcome you all for this online 6 days FTP program. I welcome our Chancellor Ayya, Srinivasan Ayya sir, for this program. My heartfelt welcome to our dynamic principal sir, Dr. D. Shanmugh Sundaram, for this online FTP program. And next, I welcome our COE sir, Dr. K. Velmurugan sir, and our Dean Academic sir, Dr. K. Anbarasan sir, and our department head, Dr. R. Gopi sir, and our other faculty members for this session. Last but not least, I welcome all the participants, research scholars for this event. Once again, I welcome you all. Sir. Overview of DSEC. Dhanlakshmi Srinivasan Engineering College, an autonomous institution, has 22 years of enacting education, as established in the year of 2001 at Perambalur, Tamil Nadu. Our institution is accredited with A grade by NAC in the year of 2015, and further it was accredited with A grade till 2025. Our institute is conferred with autonomous status from UGC and Anna University for a period of 10 years from 2020. Our college is accredited by TCS. Departments of Aeronautical Engineering, Biomedical Engineering, Computer Science Engineering, ECE, EEE, IT, and Mechanical are accredited by NBA. Our institution is run by the Silver Jubilee Celebrated Group of Dhanlakshmi Srinivasan Charitable and Educational Trust, Perambalur, Tamil Nadu. Our endowed educational trust started the college with the motto of promoting engineering and technical education to the students in the rural area of backward districts of Tamil Nadu. And our institution offers 16 UG programs and 6 PG programs. The aspirants of the institutions, both the faculty and students, are vibrant in congregating the cutting edge technologies in their respective fields. And their motto is aided by the regular professional society and club activities. And it offers a good scope for service oriented programs organized by NSS, Fine Arts Association, and Student Care Center. The rainwater harvesting units are also built with a societal impact in our college premises. The Human Resource Development Center focuses on full-fledged placements for all department students. As now, with another great milestone of receiving autonomy, and we are looking together with the hope of consequential development for the students in all aspects. And we have also introduced some skill-based module which help our students to mold themselves with a variety of skill-based learning techniques. And these courses are designed to groom the budding engineers to become an employable and responsible citizens of the nations. Regarding infrastructure, our campus is a lush green campus and has well-equipped laboratories and smart classrooms. Separate hostel facilities for both boys and girls with multi-cuisine food and 24 hours Wi-Fi facilities is also available in our institutions. And also we have a specialized central auditorium with fully air-conditioned facility and having a seating capacity of around 2,500 with the state-of-art facilities. High competent faculty with industry and academic experts caters the needs of the students on curriculum, which help them to meet the global challenges and the needs of employers. Project-based learning is incorporated to equip research skills among the students, and various activities are performed by our institution in a student-centric basis, such as continuous assessment, assignment strategies, students' initiative materials, etc. Regarding training and placement, personality development program classes are organized to ensure the transformation of the student as campus to corporate level, and nearly 85% of the students were placed in reputed industries like TCS, HCL, Sutherland, and etc. Moreover, we encourage the spirit of entrepreneurship and empower the student to share ideas and develop creativity through project-based learning also. We provide the scope for the students to participate in various level of extension activities such as NSS, fine arts, sports, club activities rather than academic competency. Each and every year, we organize student exchange program through professional societies such as IEEE, IST, BMSI, and so on. National and international conferences, symposium were also organized to enrich the technical competency of the students. We have regular practice of applying proposals to funding agencies in which we have received a fund on wardrobes, SPDC, and for organizing symposium and conference, etc. With this, I'll give an overview of our department. Department of Computer Science and Engineering was established in the year 2001 with an UG course of intake 60, and we have also ME course with an intake of 36. The department has recognized as a research center in the year of 2023 for carrying out the PhD program by the Research College under Anna University, Chennai. And it was accredited in the year of 2024 for the period of 3 years from 2024 to 2027. It has a dedicated and specialized faculty members in the different areas like deep learning, machine learning, cloud computing, artificial intelligence, quantum computing, networking, etc., with a rich expertise in academics, industry, and research. The department has a well-equipped and spacious laboratories with modern computer equipments, and we have also organized many national and international conferences, symposium, workshop, project expos, and many other events. Our student has also placed in many companies like Cognizant Technologies, the Tata Consultancy Services, HCL, Renault Nissan, Sutherland, etc. Overview of FTP. FTP Overview of quantum computing, FTP, 6 days, AICT sponsored online FTP program. In our FTP program, more than 420 participants like academicians and research scholars of diverse discipline in engineering from far and wide across the country was registered. And the main goal of faculty development program is to cover an extensive area of multidisciplinary topics in quantum computing. And it is a 6 days virtual program comprising of technical tasks, talks, and hands-on training sessions delivered by both academics and industrial experts. And the today's session is about quantum computing basic concepts and global perspectives, which will be delivered by our resource person, Dr. J. Jayanti Ma'am, Professor, Department of Computer Science and Engineering, Sona College of Technology, Salem. And once again, it's my pleasure to introduce our today's resource person for this online FTP program, and who is going to deliver the session about quantum computing basic concepts and global perspectives. Dr. J. Jayanti Ma'am, Professor, Department of Computer Science Engineering, Sona College of Technology, Salem. At present, she is working as a professor with more than 20 years of teaching experience in Sona College of Engineering, Salem. She has completed her UG degree program, BE Computer Science Engineering in Government College of Technology, Coimbatore, in the year 1999. And she has completed her PG degree program, ME Computer Science Engineering in Sona College of Technology, in the year 2007. And she has completed her PhD program in Government College of Technology, Coimbatore, in the year 2015. And her areas of interest are software engineering, artificial intelligence, database management system, machine learning, data science, software testing, object-oriented programming, and agile methodologies. She has also received a Best Woman Researcher Award from SCT Women Empowerment Cell and also received Pudumai Pen Award from Tata Group. She has published 29 research papers in international journals, and she has presented 20 papers in international conferences and presented 13 papers in national conferences, and has also organized many national conferences, symposiums, workshops, and hands-on training in her various areas of interest. With this, I welcome such a great personality for this wonderful session and to make this event a grand success. Once again, welcome you all for this Atal 6 days online FTP program. I welcome you, ma'am, and welcome all the participants for this online FTP program. Thank you.
Thank you, Geeta ma'am. Thank you for your wonderful welcome address. Dear participants, one more thing, the attendance is very, very important for these 6 days FDP. So I request you all to attend this session, useful session for quantum computing topic. And at the end of the day, we have a quiz examination for all the participants, and we have a feedback session for the last day. So I request everyone to attend the session without fail to learn recent trends of quantum computing. Thank you. Thank you everybody for attending this session.
Thank you, sir.
The session will start within 20 minutes. 6:30, ma'am will start a session for basic concept of quantum computing. Participant, during the session, if you have any clarification, kindly message through the chat box. We will rectify the problem. What are the questions you are asking through the session? And moreover, if you need the end of the session, we will share the PPT to your mail ID also. So if you have any clarification, kindly message through chat box. Ma'am, Jayanti ma'am.
Yes, Gopi, I have shared the
Yes,
presentation.
ma'am.
Is it visible?
Okay, ma'am. Yeah,
Yeah.
visible, ma'am.
वॉइस ये तो मेरी वॉइस
Excuse me, sound is not available these slides. Not audible right now.
madam voice are not audible madam.
Also, don't show any type of the PPT.
Ma'am, screen not yet shared and also no.
Hello, good evening to all. Session not yet started. Please wait.
Okay, thank you sir.
Thank you.
Ma'am, you can start now.
So good evening all.
Yes, ma'am. Good evening.
Am
Good
I
evening, ma'am.
audible?
Yes, ma'am.
Yes, ma'am.
Audible.
Yeah. So
Yes, ma'am, audible.
yeah, it's my pleasure to host this program as a part of Atal FDP, which is being hosted by Dhanlakshmi Srinivasan Engineering College. It's my pleasure to thank Mr. Dr. Gopi for inviting me to host this session, and his team who has done a wonderful effort behind this session. So hope all the participants are excitedly waiting to attend this session. So definitely this would be a great session for you all. So to have or to gain knowledge in the domain of quantum computing. So we know, right, which is the greatest part of world in the upcoming era. So it is the right time to learn this quantum computing technology. So before seeing this, so when we think about computers today, we tend to think about the normal electronic digital computers. Yeah, so it was introduced in the year 1940. So the first computer was in an electronical way, so it was developed. So later, slowly it was developed in various stages, and it came to an end, like it became an ubiquitous computing. So ubiquitous means like we can find computers in different ways or different sizes, starting from home needs to workplaces, and in many of the places, whenever we want to transport the computer for doing some purpose also, it is always possible. So so majorly the ubiquitous computing help us a lot in various applications. Then another greatest part of electronic computer is it's all about supercomputer, which help us to do the work to solve the complex problems in different domains, both in scientific as well as in domains which needs the complexity is very high. So whenever there is a possibility of giving solution, so we'll go for supercomputers for solving that particular problems. So we may think like we have enormous development in electronic computers itself, and starting from the home need to the scientific needs. So now how exactly the quantum plays a vital role in the world, right? There exists exactly the need. So before going into the quantum, so we'll see how exactly it finds its own way and how it evolves, where exactly the need comes one by one. So let me see. Yeah. So as we discussed, the classical computing, so two major domains came into the picture. One is the classical computing and another one is the quantum computing now. So the computing based on the normal classical physics, what we called as electronic computers, is all about classical computing. So we know, like when we use classical computing, the basic information is being stored in terms of zeros and ones. So it is comes under the category of Boolean logic for processing information. This is the very basic we all know as a computer scientist. So then we have different examples for classical computers, starting from desktop PCs, laptops, and our smartphones and servers. which has been used for different purposes. Then we know, right, there are various key components of classical computer. So starting from our CPU, which is doing some kind of process. Whenever we need to do a process, we need a CPU. Then for doing a memory part is the greatest role in our classical computer. Then storage, we have primary and secondary. So normally the program in execution and whatever is being processed, that will be kept under RAM, and the remaining data will be stored in the secondary storage. In addition to that, in order to do any application in a full-fledged way, we need a peripheral devices which contributes to our input and output devices, like keyboard, mouse, monitor, and printer, all those things. These are all the parts of classical computers we know, right? So the basic thing, working principle of classical computers are, it depends on the binary system. So again, the information is being interpreted in terms of zeros and ones. Then it's been used in terms of logical gates. The zeros and ones are being interpreted with the help of the logic gates. Again, the logic gates are implemented with the help of transistors. You just understand the hierarchy, how exactly the information is processed. So the information, whatever is being given by the end users, are being treated by a machine in terms of zeros and ones. So the zeros and ones are produced by logic gates. Again, the logic gates are being implemented with the help of the transistors, we know, right? The transistor is a kind of switch kind of thing. Whenever you pass a signal, if it is in the on condition, it just passes the signal to the respective output, and if it is closed, the output will be zero. Okay, so this we all know, which is the very basic system. Then the classical gates also we know. So this session is a basic session on quantum. In order to understand the quantum, we have to refresh the basic classical computers. So I covered all these things. So classical gates, again, we have different types of gates. Buffer, which is the simple type, whenever you pass a signal, input signal. So if you pass 0, the output will also be 0. If you pass input as 1, then the output will also be 1. Okay. So then NOT gate, which inverts the signal. If you pass 1 as an input, then it just inverts and produces the output as 0. Okay, so OR gate, you know, right? If we pass any one of the input is 1, then naturally the output will be 1, otherwise it will be 0. AND gate, which is like if both of your inputs are high, then the output will be high, otherwise it will be 0. XOR, either one of the input out of 2 will should be 1, then the output will be 1, otherwise if both are same, then the output will be 0. These are some of the basics we have to recall. Then in normal cases, whenever we have to find out or we have to design a circuit to solve certain problem, we should be having 3 different items. One is the logic gate, second one truth tables, third one is the logical expressions. Actually, the problem which we want to find solution has to be framed as a logical expression. See, for example, I need the combination of output as 1, 0, 0. So if I want output as 1, 0, 0, first of all, I have to find for different combination of inputs. Okay, so to get the output as 1, 0, 0, I have to design my logic gate circuit. I have to design my own circuit by having different logic gates. Okay, so when I build my own circuit, then based on the characteristics of a particular gate, when it receives the input, then naturally it produces the corresponding output based on its characteristics. So from the output, whatever we are deriving, the truth tables will be derived. Okay, so then via the truth table, we'll ensure that whether we are getting the expected output for the problem to be solved. This is the normal way of constructing the classical circuits. You might have remember our half adder, full adder circuits, and the circuits for doing multiplications, basic computations. There are circuits we have studied in the both PG and UG curriculums. Okay, so now, so you might have remember, like the classical computing was evolved from the early computers, like from the mechanical calculators to vacuum tubes. Then it's been evolved to transistors, Then it was changed to the next era, like integrated circuits. These are the various ways it was evolved. Then now the very important law which takes a very important role in quantum too. Okay, so now the greatest question is, I have a classical computer, it is having the various potential to solve different types of problem. So I have the ubiquitous computers, as well as I have supercomputers which is having the different power to solve different types of problems, right? So now the question is like, so I'm having the very good supercomputer, and I'm having the normal computers for solving the day-to-day problems. Then why should I go for quantum computers? Can I pose the question here? Any volunteer answer from here? So I have the supercomputer which is having the enormous power. So in addition to the supercomputer, why should I go for quantum, which is again doing some powerful computation and give us results in a very appropriate way?
We cannot get the combination of 1 and 0.
You cannot get the combination of 1 and 0. Okay, why should you worry about 1 and 0?
Ma'am,
Even if I'm having 1 as a separate output, 0 as a separate output, so I'm doing wonderful job using classical computing itself. Why should I have both state? Why
Hello,
should I
ma'am.
have 1 and
Hello.
0, and
Hello.
why should I get confused?
Actually,
Hello,
supercomputer, it only works on either 1 or 0, but in quantum, we can use both 1 and 0.
Yes, sir, that's the difference between the quantum and the classical way of computing. That's there.
Hmm.
It's already there. It's true. But why should we worry about? Why should I have 1 and 0 simultaneously?
hello,
To
ma'am.
increase the functionality. For example, work will be there. If normal computing, classic computing, it takes too much time with too much of computing power. But here
Yeah,
in quantum, with same computing power, we can achieve more productivity or end result.
yeah, that's good.
It may be improve the quality of the functions.
Pardon, sir.
I think.
Pardon, sir.
Quality
Can
of
you
the
repeat?
function.
Yeah.
Madam, it solves problems that are too complex for traditional computers.
Ah. So I hope, sir, I hope the for supercomputers are being used in, used in ISRO for solving the scientific problems too. Only the recent years, only the year after 1980, the idea came into the picture, like quantum is one of the mechanism which could be useful for computation. Previously, it was like even the supercomputers are done the wonderful job. Yes. So I have a very good answers. Thank you, participants, for your wonderful participation. So the basic thing which you should remember is like, whether it is an evolution of any electronic device or computational device, the basic is the Moore's law. So hope you all remember. The Moore's law says that the number of transistors on a chip, which is being doubled approximately in every 2 years. Which means that, see, for example, if I'm designing a circuit, if I'm designing a circuit with some 50 transistors for solving some problem and providing solution. So I'm designing a circuit with 50 transistors for providing a solution to certain problem. After 2 years, if I'm going for solving similar type of problems, and I need to design a new circuit for solving the problem, in that case, so what is the requirement now? So it doubles the need of transistor. Suppose if I have used 50, after 2 years, I have used around some 100 transistors for providing solution for similar kind of problems. So it was the law which was given by Murray. Okay, so but it works well. It works well for a long time. Okay, it was really a wonderful law, and it works well without any difficulty, and it was realized in the real world applications in most of the times. So it actually at one point of time, if you all remember, like the transistor from the semiconductor to next level, next level, next level. Now the size of the transistor would been reduced to the level of atom. Okay, to the atom level, the size of the transistor was reduced. If you reduce the component size and if you'd like to accommodate inside the circuit, that's good. I could accommodate many number of transistors inside the board and I could perform the wonderful operations and I could get the output. But you just think of the heat dissipation. You just
Ma'am, your voice not.
Ma'am, your voice not audible, ma'am.
Ma'am, your voice is not audible for all.
Ma'am, your voice is not audible. I think you are on mute.
Hello, madam. Your voice is not audible. Please unmute that one.
திடீர்னு ஓடுது நெட்டு. அது என்ன பண்றது? சிக்கனமா எப்படி யூஸ் பண்றதுன்னு தெரியலையே.
say, am I audible?
Yes, ma'am, audible, ma'am. Okay, you can continue.
So which point you were not able to hear?
Ma'am, slide number can go. Wait, ma'am.
Number 8, ma'am.
Slide
E
number
for
8, ma'am.
quantum. Yeah.
Slide number 8, ma'am.
Slide number 8. Okay.
Okay.
Now the
Evolution of
slides.
classical computing.
Yeah. Is it shared?
Yes, ma'am.
Yeah. Okay. So the evolution I've started with, like, so we had a abacus and the basic mechanical calculators was introduced. Then we moved on to vacuum tubes. Then it's been moved on to transistors and integrated circuits that we know. So I explained about the Moore's law, right? The Moore's law works well till some point. Like he says about the number of transistors which are used for ICs would be increased double the time in every 2 years. So it works well for a long time since the size of the transistor was being reduced till an atom size. So now it's when it getting reduced too much, so the problem might have occurred in the chip whatever we are using. So the main problem is the heat dissipation among the transistors, as well as there are a lot of other problems to occur. For giving cooling effect to the integrated circuits is also very complicated issue. So there is a need for a quantum because of two reasons. One is the Moore's law is breaking down because of the different issues which maybe arise when you go for designing these circuits with a reduced size of transistor component. Then intractable problems is another cause which is not being solved using the supercomputers. See, for example, if you take the factorization of prime factorization of a number, up to certain number you can easily using the I mean normal ubiquitous or supercomputers, you can do things the factorization computation in a faster way. But when you increase the number size, it dramatically increases the computation power, as well as the time taken for doing the computation is very high when you see the supercomputers. So these two are the reasons why we are moving to the quantum. We'll see the things. So Moore's law, the slowdown reason for Moore's law is actually the transistors. Now we are approaching it's nearly the size of atoms, and you cannot shrink the size. So because of there are some limitations in the lithography techniques. So it is again the limitations, again heat which is being dissipated in the circuits which we are using the reduced transistor sizes being challenging one. So you have to find the cooling chips where the heat dissipation can be moderately controlled. When the heat is being dissipated, naturally the performance and the reliability of the output will also be get affected. Then the power consumption, if you have a huge number of transistors in a single IC itself, then again there is a challenge for leakage in current, which leads to increased power consumption and reduced battery life. So the major three causes: size, heat, and power consumption. Then cost. The manufacturing cost of the components which are in very miniature size would be exponentially high. So that we need to think of. Then interconnect delays. So when you interconnect different signals that moves from one component to another component, there is a greatest challenge. So these are some of the reasons why we are moving to. So whenever we are thinking of quantum, you have to think of Moore's law slowdown. Another reason is intractable problems. What do you mean by intractable problem? Is like one impossible classical computer to solve efficiently is like normal mathematical computations, like finding out the factorial of number of more than 1000 or the higher numbers. It takes months together to compute the value. It's not so like it cannot find the result, but it takes years together to find the solution. So second one is drug discovery. When I find drugs for any kind of diseases, I have to find out the way how the molecules are being integrated and how it's being combined. So the various possibility and probability of combining the drug molecules are being simulated using the classic computers, but it takes a lot of time for introducing the new drugs. Then again, the breaking modern encryption, like the greatest difficulty or challenge what we are facing now is the data and its security, right? So when we pass the data from one place to transfer data from one place to another place, so naturally the security is highly required in most of the cases. So in that case, the vulnerability to security is being, controlled to some extent by the classical computer or supercomputer. But when we go for quantum, it is completely being controllable. Then we can go for applying this quantum for in optimizing the problems in logistic domain, as well as in the finance domain. So finance, if you take like the trading and stocks trading is a very important domain of finance, like the country's economy will also be decided using that. In that case, the AI and the quantum plays the vital role. Then simulating quantum systems. See, nowadays what we are doing is only the few companies are involved in building the real quantum systems, like companies like IBM, Google, and they are very much interested in having the actual quantum systems for doing the computations. Others, what they are doing is they just wanted to know how exactly the computation is being happening. So the simulation they are trying to see, and see, when we have need to compute data, so if we always do simulations, it is not helpful for us. Actually, we need to explore and we have to do the actual computation. So that's been done with the help of the quantum, not by simulating, but by emulating. So these are the two reasons why we are going for the quantum world. So now coming to the quantum realm, the quantum world. So it is the mind-bending principle actually. So which basically works based on the quantum mechanics. Okay. So this is being useful for solving the problems which is being challenged for a supercomputer. So that is the main thing you have to remember. Then, as you said, some of the participants have shared wonderfully, like the bits are here known as qubits. So the normal classical computers, the bits are in zeros and one state alone. Here I'm having three different states. So one is 0, another one is the 1, and again the superposition, which is known as 0 and 1. So there is a possibility of a particle which is being in both the states simultaneously. So that is known as a superposition. That is the greatest difference. Then there is another exponential power in quantum computers are. So we can apply this particular quantum concept for solving or providing solutions to different fields like medicine, material science, and artificial intelligence. So to understand the quantum completely, we should know the quantum mechanics basics properly. So here I just wanted to know, now I hope all the participants will come to know how exactly we are moving to the classical computing scenario to the quantum scenario. See, the major two reasons are, one is Murray's last load, another one is the giving solution for intractable problems. Hope you all, so till this point, I think you all comfortable. If you don't, so you can, I'll just pass for a few minutes, then I'll proceed. If you say okay, I'll proceed.
Yes, ma'am. Okay, ma'am.
Okay, ma'am.
Okay, madam.
Yeah, yes.
Okay, madam.
Okay, ma'am.
Yeah, thank you. Yeah. So in order to understand the quantum in a very better way, so we should know the basics behind this, which is one thing is classic physics and another one is the quantum physics. So till now, most of us are very good in knowing the classical physics, but quantum physics then and there we might have known, but we are not that much familiar with quantum physics. You just see the difference. Like classical physics, normally when we see some objects, okay, so that is in the macroscopic world. So if you see a car, if you see a laptop, if you see a particular object evidently, so then it is called as a classical physics will talks about the macroscopic world, which always talks about some everyday objects. Then always when you go for the classical physics, it is always the outcomes are predictable and deterministic. Okay, outcomes are predictable and deterministic. So if you give this input, then this would be the output. That is very much deterministic. Then example is like the Newtonian mechanics, which is nothing but the planet orbits around the sun is a very good example for Newtonian mechanics. Like the sun is being surrounded by various planets, and every planet is being rotated in their own orbits, right? That itself is a Newtonian mechanics, which is having its own rules and regulations to be followed when it rounds the sun. Then electromagnetism is another very important principle which is being followed in most of the electronic devices and most of the principles. So when you apply these things, then it's been comes under the classical physics. If you go for the quantum physics, again it enters into the microscopic world. So it is having two major items. One is the atom and another one is the subatomic particles. Two things. One is the atom and another one is the subatomic particles. You know, right? The subatomic particles are nothing but, we know, right, familiar with electrons, protons, neutrons, and now one more thing is added, which is called as a photons. Okay. The photons are the particles which are emitted from the light. So whenever we think of quantum physics, you should know about atoms as well as subatomic particles. The subatomic particles, which covers electrons, neutrons, protons, as well as the photons. See, photons are the particles which are emitted from the light source. Okay. So when we speak about this microscopic world, which is always a probabilistic nature and counterintuitive. The word counterintuitive is having its own value. It means, so when you go for the classical physics, when you give some input, you know what is the output. Okay. But when you go for the quantum physics, from the output, you could able to find out what are the possible input. Okay. So this is the case. So I think you can find the difference. So the quantum physics is having the characteristics of probabilistic and the counterintuitive case. The counterintuitive in the sense, from the output you can able to find out what are the possible inputs. Okay. So then we have seen the examples for classical physics, which is the Newtonian mechanics and electromagnetism. But in the case of quantum physics, so I'm having the example as wave particle duality, superposition and entanglement. Okay, these are the jargons you might have heard. Some of you might have heard already, but some of you might have heard first time. So wave particle duality, what does it mean? So it means like, so when you do certain action, when you do some operation, so the outcome would be produced as a wave. Sometimes, so it will be produced as a group of particles. Okay, it will be produced as a group of particles. So when you go for the quantum, this wave particle duality plays a vital role. Sometimes it follows the wave principle. Sometimes it follows the particle duality principles. That's why it is called as a wave particle duality. The second important, we will see one by one in a detailed way. Second one is the superposition. Superposition is the position we have seen light. When a particle is there in both 0th and 1 position, that is known as a superposition. Okay, 0 and 1 state. You may not be able to find out whether it is in 0 state or in 1 state, then that position is known as a superposition. Then entanglement is a very good concept in quantum, which is if one particle that exists in one part of the world, there is a correlated particle which may again exist in the another part of the world. Okay, so if one is representing some characteristics, then naturally the other will also be representing the characteristics. I'll explain you in detail in the upcoming slides. So, but this is the basic difference between classical physics and the quantum physics. Okay. So the quantum physics normally, see here, I have explained already you. So which consisting of the energy, momentum and other physical quantities are often restricted to discrete values. So here the wave-particle duality plays a major role, which exhibits both wave-like and particle-like behavior. So then superposition, the quantum system may exist in multiple states simultaneously. So until it is measured, it is in the multiple state. Then entanglement is the concept which is being exhibited by correlated particles. Okay. So both are in the same state. If I'm having the particle 1 at one end and particle 2 in another end, but both will possess the same characteristics and same state. Okay, so that you have to understand. So that there are scientists who were working in the quantum physics like Schrodinger and Heinsberg and quantum measurement. These are the very important principles we should understand properly. Hope these things will be covered in the upcoming days. Okay. So while it's been dealt in different topics, then as I told you already, this application of quantum mechanics should be in the field of, they started using this mechanics in the field of technology, chemistry, material science, and quantum computing is the very vast and very powerful field where the computation itself is being entered in the quantum phenomena. Okay, so I mean, this is the basic difference. So qubits, to summarize, so this is the quantum mechanics. To perform powerful calculations, we are applying the quantum computing. Then this quantum computing, which is having zeros and ones, and this is known as qubits. Why? And again, it is having an extra position called as superposition, where both 0 and 1 will be in the will be treated in the same state. Then again, the quantum phenomena like entanglement allows quantum computers to tackle the problems which are intractable. Okay, so these are the things. I just wanted to play a short video here for few seconds, few minutes, to understand the concepts whatever we are studying till now in a better way.
Dave and Ryan are two computer engineers.
Is it audible?
Who decide to play the game of flip the coin.
Yes, ma'am.
Yes, madam.
Ryan decides to observe this game. The computer plays the first move, but Dave doesn't know what it was, either heads or tails. Now on his turn, he can either choose to flip the coin or not. And similarly, even if his results will not be revealed to the computer. Now, again, the turn goes to the computer, and after playing a few rounds, the computer reveals the result. While observing all this, Ryan says, "Hey, do you know that?" Dave and Ryan are two computer engineers and best friends who decide to play the game of flip the coin on Dave's computer. The computer being the opponent, and Ryan's game. The computer plays the first move, but Dave doesn't know what it was, either heads or tails. Now on his turn, he can either choose to flip the coin or not. And similarly, even if his results will not be revealed to the computer. Now, again, the turn goes to the computer, and after playing a few rounds, the computer reveals the result. While observing all this, Ryan says, "Hey, do you know that there is only a 50% chance that either of you will win?" Dave got curious. He asked how he knew. Ryan explained that it's a computer, and he just tried to analyze its moves. But suddenly, he says, "What are your chances if you play the same game on quantum computer?" Dave was confused and asked, "What is a quantum computer, and how is it different?" Quantum computers are advanced machines inspired by quantum physics, a study of the behavior of atoms and particles. So, quantum computers operate by studying and controlling the behavior of these particles, which in a way completely is different from our regular computers, or even supercomputers. It is an upgraded and powerful version of these computers, but not exactly the next generation computers. Like bikes, you cannot build a better bike just by building and adding more and more cycles together. Although they both share almost the same functioning. Dave further questions, how does it work? Ryan comes forward and explains to Dave that while playing Flip the Coin, his computer took heads and tails as bits of 0 and 1, and depends on only these two results. While the quantum computer, on the other hand, will also have these possibilities, including a possibility of a mixture of both heads and tails, like 0 and 1, for example, with some portion of 0 and some portion of 1. And due to this fluid possibility, it increases the chances of you losing the game. Because whether you choose to flip the coin or not, the outcome will still be there between both possibilities. Just like a mixture of lemon juice with water, even though the portion of lemon juice is very little in that mixture, you can't say that it is not there. This property of superposition and entanglement of quantum physics empowers quantum computers to handle operations at speeds that are orders of magnitude faster than traditional computers, while using a fraction of the energy. Upon understanding this, Dave was mesmerized by the concept of quantum computers. Quantum computers aims to revolutionize more future quantum technologies. And just like other transformations around the world, quantum computers have the potential to impact our lives in so many ways, like our security needs, healthcare needs, etc. For example, it can be used to create private keys for encrypting messages from one location to another. It can be difficult for people with ulterior motives to copy the key of quantum uncertainty. This type of unique and unbreakable encryption is already tested by banks and companies like JP Morgan, Wells Fargo, Barclays, etc. It can be used in the medicinal world, as it will be easier for quantum computers to study each property of atoms and molecules, as it works on a similar concept. So, here is a question for you. What makes quantum computers different from supercomputers? A. Atoms and molecules. B. Uncertainty of outcomes. C. Algorithm. D. None of the above. Please give it a thought and drop your answers in the comments section below. 3 lucky winners will receive Amazon gift vouchers. Due to its benefits, currently, it is connected to over 17 billion devices globally. Quantum computers are the future of our coming generations. Although it is still under research work, it is still taking over the technology and the business world. Companies like Google and Microsoft are competing to build quantum computing tools. This progress could allow some of the benefits and insights of quantum computation to be realized long before the search for a large-scale, error-corrected quantum computer is complete. We hope you enjoyed this video. If you did, a thumbs up would be really appreciated. Here's your
So how do you find this video as?
Yeah, interesting, madam.
Yeah. So again, it's been explained, right? So we'll take one example. I do not know how far you people understood. Some of you might have properly understood. Some of you may have doubts again. So when you flip a coin, so in a classical way, we'll think either we'll get head or tail, right? At any point of time, we'll get head or tail, only 2 possibilities. If if a system and a person is playing, then if system is getting head, then naturally the person will get a tail. Then that is the deterministic output we know, right? If one person is having 0 and another person will have 1, so that is the deterministic output. When we use for the same problem to be solved, when we use the quantum, so we could see the possibility, right? So one thing you have to understand clearly here is when you toss the coin, when it moves from up to down, so it rotates, it flips many times. Okay, it flips many times. Whenever it flips, there is a possibility of head, there is a possibility of tail. So alternately it may come, right? So it may be head or it may be tail or head. So when we go for the quantum, it takes the complete probability. It studies the complete probability. So starting from the time at which I am flipping the coin to the point till it reaches the down stair on seeing the result. Starting from task and end up with the point at which I am seeing the result, whether it is a head or tail. Till that point, it flips many times and it reaches one value finally. Okay. all the flipping probabilities are calculated, and it's been finally it predicts that. So it is the output. Okay, so that is the thing which we have to understand. Yeah. So do you understand?
Yes, madam.
Yeah. So this is how it's been different. One sec.
Ma'am, your voice not audible, ma'am.
Yeah, ma'am. I'll come back. 1 minute.
Oh, sure, ma'am. Sure.
Yeah, sorry for the interruption. So we should know when we see before seeing the final outcome. So when we go for the quantum, am I audible?
Yes, ma'am. Yes, ma'am.
Yeah. Yes, ma'am. Yeah. So when we go for the quantum, so we have to see all the intermediate state changes, and finally we are seeing the results. Okay. So when we go, when we see the classical computing, it's not possible. Either it finds out whether it's zero or end results only we could able to find out. But when we think about the quantum, it always talks about the it always talks about the intermediate probabilities of getting results. So based on the probabilities, it gives us the result like whether the particular person will be winning or losing the game. This is one simple example, but it is having its own value in most of the applications. Yeah. So hope you find the video as a useful one, and I mean you could understand the things in a better way. So that is the one thing you have to remember. Then so on seeing that particular video, you have to see the difference between quantum and classical. Right? In the classical, we are having bits zeros and ones, and in quantum you have qubits where we have 0 and 1 separately as well as the combination. Then processing power is having the exponential processing power. Here it is linearly 1 by 1 it will compute. So I don't know how many of you, I'll give you one problem. Like if a particular lock is there, okay, you just assume that there is a lock which is having the digital key, okay, digital number lock. So the number lock combination is like a 3-digit number. Okay, it is a 3-digit number. So naturally the combination would be like 2 power 3, 8 combinations will be there, right? So if I use the classical computer, what it will do? 1 by 1 from 0000 to 111, 1 by 1 it will try and it will find out the right key and it will tell us the result. Okay. But when you go for the quantum, it takes all 8 combinations simultaneously at the same time, and it identifies the proper key. Okay, so that much enormous exponential power capability it is having. Okay, so the hardware which we are using in classical is CMOS circuit, silicon based, where here we are using the superconducting circuits where trapped ions and everything is the atoms and subatom particles are being used. Here the processing type is parallel. I mean always it's computing all possibilities, but here in classical computing it is in the sequential way. Then applications, everyday tasks I can use always the classical computing. I cannot go for doing simple things and all, I need not go for the quantum. But whenever there is a need for optimization, whenever there is a huge computation is required, data analysis, all those fields which requires the quantum. Then, so we have seen like qubits, superposition, entanglement, quantum gates, quantum algorithms, quantum speed up, and some other challenges are very important concepts in the quantum. Okay, qubits we know, right? It is the basic unit of information in quantum computing. So it is basically, it's been driven by the mechanical equivalent of qubit is nothing but mechanical equivalent of your classical computing. Anyway, the qubits will be finally converted into classical bit. That we will see how it's been converted. So the classical bits will have the states 0 and 1. I mean, when you compare the 0 and 1 to the light or switch operation, when the light is in on state, it is 1. Then when the light is in off state, it is 0. The same light, you just think of when the same light, when you compare it for the qubit. So when you switch on, okay, when you switch on the light, and it'll move from off state to on state, right? It will move from off state to on state. So when it moves from off to on, there are some transition which is happening, right? But we never realize and we never tries to analyze them. But when you go for using the quantum, in that case, what you have to do is, when it moves from off to on, so it slightly increases its light eminence, right? Brightness from dark to brightness it converts. Okay. In that also there is the from low brightness to original brightness it comes out. Okay. So that state we never think of, right? When you go for qubits or when you go for the quantum, it computes all the way how it becomes dark mode to light mode. Okay. So that you have to remember that position which is being always in intermediate state. So in most of the places, the particles are in superposition. You may not know, right, whether it is in the zeroth state or in one state. Okay. So that is also very important characteristics of qubits. So here, so there is a way how exactly the quantum property qubit has to be interpreted. So you know, right, superposition is the combination of both 0 and 1 at the same time. So here you just assume that a light switch being both on and off simultaneously until you observe it. So before we observe it is on, it is come across some intermediate state, then it comes for the on state. Okay. So you just assume that the north pole is having 0th state and south pole is having the 0th state, and this one is having the 1 state. Okay. In between there are some state changes and it reaches to 1. Okay. So here what you have to understand is, before it reaches to 0 to 1, it come across multiple states. Okay. So every state is being interpreted in a vector form. Every state in the axis being interpreted as a vector form. Okay. At any point, if you see, it may be in superposition or it may be in 0th position or in 1 position. Okay. So when it reaches to 0 to 1 or 1 to 0, it come across many multiple state transitions, then it reaches the final state. That you have to remember. Okay. So let me play a video here to understand the superposition in a better way. To visualize it, it may be useful.
Superposition is a fundamental principle of both quantum computing and quantum mechanics. The principle of superposition states that a physical system Superposition is a fundamental principle of both quantum computing and quantum mechanics. The principle of superposition states that a physical system can exist in a sum of its possible measurable outcomes. When talking about the superposition state of a quantum bit, the only possible measurement outcomes are 0 and 1. Writing this down mathematically would look like this, where the coefficient squared would represent the probability of measuring the qubit in either 0 or 1. Once we physically measure the qubit, you will never find it in a superposition state. It will only ever be in the classical states of 1 or 0. We can never directly measure a superposition state. Quantum mechanics forbids this, but we can deduce it from the outcome of specific experiments. In Qiskit, you can put a qubit into superposition by applying a Hadamard gate. See the links in the description to learn more.
Yeah, I think you can understand certain things like when superposition is a linear combination of zeros and one. So here I have written an equation, right? This is known as a bracket notation. Okay, bracket notation, and here you have two numbers, alpha and beta are complex numbers, which knows the probability alpha and beta. So this is the bracket notation to represent to find out the value of superposition. Okay, so here I am having alpha to represent the probability of 0 becomes true, and beta represents the probability that 1 becomes true. So this both alpha and beta are complex numbers. So when you go for the quantum computing, this complex numbers play a vital role. Okay, so using these complex numbers, the vector is being represented, and using the vectors and the unitary matrix only, we could find out the probability of measuring the qubit, either in which state and which state it leads to. Okay, so if I want to know the probability of measuring qubit 0, what is the probability? I have to find out mod of alpha squared. Okay, mod of alpha squared. So the mod of alpha squared, what it does is, which gives, if it is measuring the qubit, it is the value which measures the qubit 0 as probability, and beta square will gives the probability of measuring the qubit as 1. Okay, so this is the very normal equation, so which is being used for measuring the probability that the bit becomes 0 or 1. So here, so I'm introducing a new word here, Hadamard gate. So this is the gate which using which I can find out at any point of time what is the chance of measuring the 0 to be the value, or what is the chance of measuring 1 to be the value. Okay, so this I will show you. I mean, when you come across the quantum gates, they will explain you in detail. Anyway, some of the gates I'm explaining in the upcoming slides too. So see here, this is the block sphere. This is the block sphere. This sphere, if you see, it's having north and south pole. The north pole, which indicates the value 0, and the south pole indicates the value 1. So in the sphere, if you take any line, any arbitrary line, so and if you draw any vector to find out the particle value at particular position, I have to use the vector concept. Okay. So to visualize the qubit state, I have to use this block sphere. I have to use this block sphere. In the block sphere, I'm having north pole. I'm repeating. I'm having north pole and the south pole. North pole, I'm having the value as 0, and in the south pole, I'm having value 1. At any point of any orbit, if I find out the particle state, okay, in that case I have to draw the vector. So so what I have to do is, that gives me what is the probability of that particular particle to get the state as 0 or to get the state as 1. Okay, so in that way I have to calculate the value. In that way I have to calculate the value. So do you understand?
Yes, ma'am.
Yeah, this block sphere is helpful to visualize how exactly the particle state value is being interpreted. Yes. So superposition or the value how exactly for the qubit is being calculated, we have seen. The next important concept is entanglement. Okay. So some of you are speaking, please mute your audio. Some noise is coming. Yeah. So quantum properties, the another property is entanglement, so as we all know. So there is a qubit A in some place. Okay, the distance apart. The distance is not a matter. And there is a qubit B. Okay, these two are having correlated. If qubit A is having some state, this state will have an influence on state of the qubit B. If you know the state of A, I could able to say what is the state of B. So that is known as entanglement. So I repeat, okay, the state of one entangled qubit is instantaneously determines the state of the others. The distance is not a matter. See, I can give you a very classical example for this. Suppose you have the socks. Okay, every day we are wearing socks, right? So I'm having the socks for left hand and left leg as well as for the right leg. Okay, so for the left leg socks, you put inside the box and you are just giving to your friend, and he doesn't know whether that box is containing left leg socks or right leg socks. He just taken that box and went away. And after he went away, you just open the socks. Okay, I mean he opened the box and see he's having left leg socks. Okay, naturally what he assumed, what he understood, the another socks which is having by his friend is the right leg socks. Okay, so wherever he goes, if one state of one object is identified, with the help of that state, I can able to identify state of the another object. So that is known as an entanglement. So qubit is having that wonderful concept. So this entanglement is being useful for doing the, in the field of cryptography, it plays a vital role. We used to, we all studied the RSA algorithm in cryptography, right? So we used to have private and public keys. So when you have the, when you are confidential in giving the private keys, so using the public key, the receiving end, the person may comes to know this would be the private key with the help of the quantum entanglement property. Okay. So the way, and again it is very, very, very secure, like the possibility of all possibility of finding out the private key is very, very complicated task. So it is highly secure. So that is about entanglement. So I told you, right? So you can, if you have a gloves for one hand and another hand, if you have a another gloves, when you travel from one place to another place, if you know the gloves of one hand, your friend may come to know what is the gloves of his friend is having. So this is very real-time example you can have. Okay. So entanglement in case of real-world implications, it's very crucial, and you see, when you go for the technological examples, it is very much useful in teleporting information like one place to another. So it is very much useful. If you send one information, they could able to know this would be the information they would like to send. So in the field of cryptography, it plays a vital role. So let me play a video again to explain the entanglement.
एक मिनट जरा इधर आइए। अगर आप यूनाइटेड स्टेट्स के वीडियोस ही देखते रहोगे तो गोला पर यूनाइटेड स्टेट्स वेकेशन वाले। Imagine you're on a long drive when you suddenly hear your stomach begin to grumble. You decide to head to a fast food drive-thru and you order a hot dog and a hamburger. They are put in similar boxes and handed to you through the window. You have no way of knowing which box has the hot dog and which has the burger. Obviously, once you open one of the boxes and see a burger, you will immediately know that the other one has the hot dog. This means that the hot dog and the burger are entangled in a certain way. This is roughly the idea upon which quantum entanglement is based. Look around you. Everything you see, perceive, and interact with in the real world follows the rules of classical mechanics. This is a study of the motion of bodies in accordance with the general principles first laid down by Sir Isaac Newton. But what about objects that are really, really small? Do they also follow these same laws of classical mechanics? Believe it or not, the answer is no. When things get that small, quantum mechanics takes over, and things start to get extremely weird. Quantum mechanics is the language of tiny particles like photons, the particles that make up light, and the particles inside an atom, such as protons, neutrons, and electrons. To give you a rough idea as to the size of these particles, consider this. The tip of a needle is so large that it could fit billions of electrons. That is how incredibly small electrons truly are. Now that you have a general idea of the size of electrons, let's talk about identities. If someone were to ask, "Who are you?" what would you say? Probably your name, right? Now, let's assume that an anthropomorphic raccoon from another planet asks you the same question. What would you say then? Perhaps, "I am Peter Quill, a human from Earth." In this case, you specify 3 levels of identification. Similarly, in a 3D space, X, Y, and Z coordinates are used to specify an object's exact location, as no 2 objects can have the same X, Y, and Z coordinates. If you consider a 4-dimensional space with time, t, as an additional dimension, then no 2 particles can have the same 4 coordinates. In the same way, an electron has 4 levels of identification, consisting of 4 quantum numbers. Every electron within an atom has a unique set of quantum numbers. No 2 electrons can share the same combination of 4 quantum numbers. Electrons can be identified using these 4 quantum numbers, which are called the principal quantum number, the orbital angular momentum quantum number, the magnetic quantum number, and the electron spin quantum number. All of these quantum numbers are very important as they help determine the electron configuration of an atom and the probable location of electrons within that atom. However, for the scope of this video, we're only going to talk about the electron spin quantum number. The definition of spin is the intrinsic value of the angular momentum of a fundamental particle. An electron can either have a positive spin, called spin up, or a downward spin, called spin down. Now, this is where things get bizarre. When we say an electron has a positive spin or a negative spin, it doesn't mean that the electron is actually spinning. Although it does have angular momentum and proper magnetic orientation, it's not exactly spinning. It may actually exist in the state of superposition when it has both a negative and positive spin. You may find the idea of superposition confusing because this doesn't seem to go along with our perception of the real world. To help explain this a bit better, here's a famous example for understanding superposition. You might have heard of Schrödinger's cat. This is a famous thought experiment devised by Austrian-Irish physicist Erwin Schrödinger. It goes something like this. Imagine that you put a cat inside an opaque, soundproof box, along with a radioactive substance, a vial of poison, and a Geiger counter. If the radioactive substance decays, then the Geiger counter triggers a setup that releases the poison, thus killing the cat. However, the decay of the substance is a random process, so there's no way to predict when it will happen. And that is why, before opening the box, you can say that the cat is in a superposition of being both alive and dead at the same time. In the same way, when a coin spins on a flat surface, it's in a state of superposition between its 2 faces, heads and tails. Similarly, electrons in their natural state exist as a superposition of both up and down spin. Only when measured do they give a definite value of up or down, which in technical terms is referred to as the collapse of the wave function. In quantum mechanics, wave function collapse occurs when a wave function, which was initially in a superposition of a few states, reduces to a single state due to interaction with the external world. When a pair of electrons are generated, interact, or share spatial proximity, their spin states can get entangled, which is what scientists call the quantum entanglement of electrons. Once the electrons are entangled, the 2 electrons can only have opposite spins. That is, if one is measured to have upspin, the second immediately becomes downspin. Now, we know that the 2 electrons, unmeasured, do not have a single spin, but a superposition of both up and down spin. If we were to separate the 2 electrons arbitrarily far, say we put one in a physics lab on Earth and another in a different lab somewhere in the Andromeda galaxy, and we measure the spin of the electron on Earth, we will immediately know the measurement of the one in the Andromeda galaxy. For example, if we measure the Earth electron to have upspin, we immediately know that the other electron has downspin. This information traveled instantaneously, faster than the speed of light. As one can imagine, this idea greatly bothered famous physicist Albert Einstein. It was such a disturbing realization, in fact, that he called this phenomenon spooky action at a distance. So how can this spooky action at a distance be useful to us? Well, let's start with one of the most common everyday objects, the clock. Cashback, coupons, discounts, no rates, only on Agoda. Agoda. Having a common synchronized clock is very important in today's world. They keep things in line, like stock markets and GPS systems. Today, we have extremely precise clocks, known as atomic clocks. The quantum logic clock at the U.S. National Institute of Standards and Technology, NIST, in Colorado, will neither lose nor gain 1 second in some 33 billion years. Entangled atomic systems would not be preoccupied with local differences and would instead solely measure the passage of time, effectively bringing them together as a single pendulum. That means adding 100 times more atoms into an entangled clock would make it 100 times more precise. Entangled clocks could even be linked to form a worldwide network that would measure time independent of location, vastly expanding the technology of GPS systems and telecommunication. Then, of course, there's quantum cryptography. As a kid, did you ever make up a secret code language that only you and your best friend could understand? Imagine that, but with the key to cracking the code being randomly polarized photons entangled with each other. That is quantum cryptography. Today, some tech companies use QKD, quantum key distribution, to design ultra-secure networks. In 2007, Switzerland tried out an ID Quantique product to provide a tamper-proof voting system during an election. Cashback, coupons, discounts, no rates, only on Agoda. Agoda. Imagine that you're on a long drive with a Quantique product to provide a tamper-proof voting system during an election. This system promises to be highly secure because if the photons are entangled, any changes to their quantum states made by intruders would be immediately apparent to anyone monitoring the system. Researchers at Japan's Hokkaido University developed the world's first entanglement-enhanced microscope using a technique known as differential interference contrast microscopy. Using entangled photons greatly increases the amount of information the microscope can gather, as measuring one entangled photon gives information about its partner. How about quantum teleportation? Is it possible? Yes, teleportation is possible in the world of subatomic particles, but it's entirely different from the way teleportation is depicted in movies and popular culture. Quantum teleportation involves the transportation of information rather than the transportation of matter, which is the specific type of teleportation typically focused on in science fiction. Physicists continue to delve into and understand more about the capabilities of quantum entanglement. Once we are able to fully harness this knowledge, it could potentially revolutionize every aspect of our existence. Until then, we will continue to try and make sense of the principles of quantum mechanics because, let's face it, it's a strange branch of science.
So hope you understood the concepts by visually seeing the examples.
Yes, ma'am.
Yeah. Do you all accept?
Yes, ma'am.
So shall we have some quizzes now? Some few questions.
Ma'am, I have one doubt. There is any difference between entanglement and teleportation?
Entanglement is a different concept and teleportation is an application.
Okay.
Yeah, entanglement is, I told you, right? So if you send, see, you have sender and receiver. You have entanglement is used in teleportation.
Yeah.
Teleportation is the act of sending information in a secured way. For sending information from sender to receiver, you can use in quantum scenario, you can use entanglement concept. this entanglement concept which helps us to build these strong cryptographic keys from sender to receiver so that no anonymous users can view that keys.
Okay.
Okay, only the receiver will come to know what would be the sender's key.
Okay.
Okay. Am I clear your doubts?
Yeah, ma'am.
Yeah. Any other questions?
In teleportation also, if we tell one state, we can able to determine another state, ma'am.
Yeah, that's why I'm telling. In teleportation in quantum, when you send an information in a secure way, it is called as a teleportation.
Okay.
Okay. But in
Okay.
normal way, what we will do, if you use RSA or any cryptography algorithm, we know how exactly the RSA works, and we will know if a sender is sending one information with the encrypted message along with the public key, the receiver will receive it at receiving end, and for finding out the private key, he has to do some computation, right?
Yes.
That computation in between, if somebody else is hacked, and they can also use that. When you use entanglement in the teleportation, the way how it's been encrypted is very strong, and only the sender and receiver will come to know if sender is sending this information, then this would be the key. That assumption can only be made by the receiver, not anyone else in the world. That's
Okay.
yeah. In
Yeah,
that
thank
way,
you.
in that way, entanglement is useful in teleportation application. Any other doubts? Yeah, then shall we move on to quiz?
Yes, ma'am.
Yeah, it's very simple only. So what is the fundamental unit of information in quantum?
Qubit.
It's a qubit, yeah. Then,
The qubit.
yeah, yes, sir.
Qubit.
Yeah, thank you, thank you. Which of the following is, take the second question. Which of the following is not an application of classical computing?
Quantum
Quantum.
cryptography.
Quantum cryptography.
Yeah, yeah, very good, very good.
Quantum cryptography.
Answer is D.
Yeah, yes, sir, exactly. Then third question.
The difficulty
C.
of putting more
The difficulty of
transition.
fitting more transistor on a chip.
Option B, ma'am.
Yeah, exactly. Option C.
Option C.
Yeah, exactly. Thank you.
Option C.
Yes. Next question.
Option C, ma'am.
What is
Option
encrypted
D.
simultaneously? Which is superposition.
Superposition.
Okay.
Superposition question.
Yeah.
Superposition.
Yeah, exactly. Right answer. What
Option
is
C.
the graphical representation used to visualize the state
Block
of?
sphere. Block sphere.
Yeah, exactly. Very good. Yeah. So thank you for your participation. So we'll go into one level further, step again. So see, right? The qubits is having its own property. The very notable property is the superposition. Okay. So superposition property, see here. So I'm having the qubit. So in the block sphere, in the north I'm having 0, and in the south I'm having 1, right? So the measurement, so whatever it may be, ultimately the quantum, in quantum we have, instead of bit we have qubits, but again the qubit is having the characteristics called as the superposition. The superposition, the position at which the state may be either in 0 or 1. The state may be in 0 as well as 1. Okay. That was the information, that was the study we had made. But we should know how much percentage is in 0th state and how much percentage is in 1 state. That we have to know, right? So when you have qubits, the very important task, what you have to do is, you have to measure the probability of the state becomes 0 as well as 1. What is the probability that a particle in a particular state is having value as 0 or value as 1? Okay, so that you have to know. In order to measure it, so usually this is the basic quantum circuit which we are using here, which is the qubit. So this is the qubit representation. We are here, I am giving. This indicates the measure. Then this is the classical bit. Now, what we have to do is, first of all, we have to give the qubit as an input. Then this measure will perform. What is the probability that the state will become 1 or 0? That measure, it will happen, and when it happens, it becomes the classical bit. So if a particular particle is in both 0 and 1 state, this measure will perform. So what is the maximum probability that will become 0 or 1? So that is only happening here, based on which it will be converted into classical bit. How many of you could understand this concept, or shall I repeat?
Can you repeat, ma'am?
Yeah.
Ma'am, when we have the combination of zeros and one, what is the measurement we are going to get?
See, we have seen the coin flipping example, right? When you flip the coin, when it becomes the head, when you flip the coin, so when it reaches from one state to another state, in between it is happening, many flips may happen. Okay, in that flips, it may have head or tail. It may have head or tail. So in the intermediate flips, what is the possibility that the flip may have head or tail? So that is the thing. So you have 0th state and 1 state. So when it reaches from 0 to 1, intermediately you come across many transitions are happening. When it reaches from north to south, the probability of the value becomes 1 is more. When you reach from south to north, the probability of reaching the value getting 0 is high. Okay, so this example, so when it starting from 0 to 1, this example, it shows that the state of the particle becomes having 0 value is 15%, and the particle which is having the value 1 is 85%. Okay, so how it measures 15% and 85%? It is having its own way of measurement here. Okay, it is having its own way of measurement methodology. After doing computation, it produces the classical bit either. In this case, you see, the probability of becoming 1 is 85%, probability of becoming 0 is 15%. Okay, so in that case, what is the possibility? The output become 1 is the highest possibility. So the classical bit value will be 1. Do you understand?
Yes, ma'am. Okay.
Yes, ma'am.
Yeah. So this is the basic. Likewise, you have, this is very simple circuit. If I want to do provide solution for the complex problem, it will be the combination of measures, and you may have plenty of different types of gates which are available. Okay. So we know already, right? It is using the superconducting circuits. It uses the trapped ion mechanisms, and the photons are used for measuring the state of the particle in terms of qubits. Okay, so these are all you have to know. Okay, so challenges again are when you there are some environmental interferences. If it happens, there are possibilities like the value of particle at any point, it may enter into 0th state, or it may enter into 1 state. So that are some of the environmental challenges you have to follow when you go for quantum. Okay. Again, so in the normal electronic computers or classical computers, we studied basic types of gates. Okay. And OR, NAND, NOT, buffer, like that. We have seen various types of gates. Here also we have different types of gates. Okay. So using those gates only, we have to form the circuit and we have to design the circuit. And in every stage of gate, we have to find out the qubit state. Okay. We'll see some examples. So the difference between the normal gates and the quantum gates are, the quantum gates are reversible. It means like from the output, you can find out what is the input. Okay. from the output, you know the output to be produced. But from the output, you can able to find out what would be the input. So reversibility is a key requirement of quantum mechanics. The reversible, if somebody asks you like what is the main difference between the normal classical computer logical gates and the quantum gates, so we must be in position to say that the quantum gates are reversible, whereas the logical gates are irreversible. Irreversible in the sense from the output I could able to find out the input that is given uniquely for determining the output. I can find out from the output, I can find out the input. Okay. This is one way. Another way is by deriving the unitary matrices. Unitary matrices are nothing but the matrix which are formed using the complex numbers. Okay, and those matrix are identity matrix, and it is orthogonally identity matrix. So these are all we will see when you come across. You just remember unitary matrices. You will come across in the upcoming sessions. So the comparison between classical gates and quantum gates are basic unit here is 0 and 1, whereas in quantum gates it is 0, 1 and superposition. So classic gates, you have Boolean logic, here you have a quantum logic. So the main operations we are performing in classical gates are AND, OR or NOT, where in the case of quantum gates you have Hadamard gate, CNOT and Pauli gates. These are the very famous and widely used gates, Hadamard, CMOT and Pauli gates. Classical gates are irreversible, and whereas quantum gates are always reversible. And these are all deterministic. Quantum gates are probabilistic. Okay, we'll see one by one. So types of quantum gates. We have how many gates? We have Pauli X gate, which is NOT gate, Pauli Y gate, okay, Pauli Z gate, and Hadamard gate, C0 gate. These are some of the gates. Pauli X gate is equivalent to our logical NOT gate. Other gates are different. These are widely used quantum gates. Pauli X gate, Pauli Y gate, Z gate, Hadamard gate, and C0 gate. So we'll see what are the outputs it may produce. Pauli X gate. So this gate flips the state of the qubit similar to NOT gate. Okay. So Pauli X gate, what it will do? If you give 1, it turns the output to 0. If you give input as 0, it turns the output as 1. Okay. So then Pauli Y gate is, this gate also performs a bit flip. It also introduces phase change. Whatever you give as an input, this will also do the flip the input, and phase change will also do. Why? What does mean by phase change is, you might have known the sine waves, right? So normally the sine wave will be like in the up and down, it will be formed. If you want to change the phase, then it will be in the reversible way. Okay, so that is being useful at some places. That will also be performed using Pauli Y gate. So Pauli Z gate leaves the qubit state unchanged. If it is in the 0 state, it flips the phase. If it is, Pauli Z gate, you have to see carefully. If the input is in 0 state, it will not flip. Okay. If you give the input as 0, it remains in the same state. But if it will flip if inputs are in the 1 state. If you give input as 1, then it will flip. If the input is in 0 state, it will not flip anything. It just remains in the same state. Okay. Then again, very important gate is a Hadamard gate. So Hadamard gate, this gate creates superposition actually. When applied to a qubit in the 0 state, it creates an equal superposition of 0 and 1. Okay. So if a qubit is in the 1 state now, it will produce the superposition of 1, 0. Hadamard gate is the gate which helps us to create the superposition. If a qubit is in 0 state, then I need 1 state, right? So it produces 0 and 1 as an output. If it is in 1 state, so it has to be converted as an output as 1, 0. Again, it is in the superposition state. Hadamard gate, you have to remember. Then the C0 gate is a controlled NOT gate. So it is having 2 qubit gates. So it flips the state of the second qubit only if the first qubit is in the one state. So you just assume that you have 2 qubits. Okay. So in the first qubit, if it is 1, then it's changed the state of the second qubit. If the first qubit is in 0th state, it will not change the state of the second qubit. Okay. So controlled NOT gate. NOT gate, please remember. Somebody have to be unmute. Kindly unmute.
புது வீட்டுக்கு போயிட்டு வந்துடுறானா ஆனா அங்க கிடக்கு பாரு.
See, some of the participants.
Valar ma'am, kindly unmute ma'am.
Kindly mute pa.
அந்த வீட்டுக்கு போயிட்டுனா அப்பாவும் காலை வேலைக்கு போயிடாரு, நானும் வேலைக்கு நீனும் வேலைக்கு போயிடுற. இது காலை எழுச்சி ஞாயிற்றுக்கிழமை சனிக்கிழமைனா வீட்டுல நான் எப்படியுமே ஒத்தையா இருக்கிறது.
Not audible.
Yeah, shall I proceed?
Yes ma'am.
Yeah. So it is a poly X gate. We know, right? It is equivalent to NOT gate. Okay. So here the input is 1. What would be the output?
0.
Yeah. So next second example. Poly X gate again. 1 will become 0. Okay. Then here 0 will become 1 and 1 will become 0. So it creates the state of 1 0. So then create the state 1 0.
0 1.
Yeah. 0 will become 1 and 1 will become 0 here also. Poly X gate, everything is poly X gate only.
1 0 1.
Yeah. No. So there is only one difference, right? Poly X gate we have seen. If it is in one state, it will not flip. Okay. Triple 1. Here also 0 or 2 zeros will become 1 and 1 will remain same. Control node. So if the control node value is 0, listen here, C0 gate 0 will become 0. If this value is also 0, then there is no change. 0 0 will be produced. Here 1, okay. Again 1 is here. Here it is 0, okay. If it becomes 1 only, it will do the flipping action. Otherwise, it will not do the flipping action. So this is X is known as a controlled node. This is a control node. So shall we move on to the practicals for some time?
Yes, ma'am.
Yeah. So can I call my scholar Naveen Raj?
Hello, ma'am.
Yes, Naveen. Could you please share the at least 2 or 3, 4 simple exercises that we can make it practically now?
Sure, ma'am.
Yeah. So shall I stop sharing here and you can share the screen?
Thank you, ma'am.
Yes, sir. Yes, sir. No, I'm just coming back again. Now my scholar is sharing you the practical exposure on this particular gates. I just come back again.
Okay, ma'am.
Yeah.
Okay, good evening all. Whether my screen is visible?
Yes, sir.
Yes, it is
Yes,
visible.
sir. Yes, sir.
Okay, myself Navin Raj. Okay, I'm going to continue this session with few examples. Actually, I have used a. Okay, so there are some softwares or tools we can use to simulate the quantum circuits. Even if we don't have access to quantum computer, so there are some softwares. So Google is providing SIRP tool. Okay, it is developed on
Sir, this
Python.
is particular tool or this is the simple open
It
window?
is just a package. IBM also providing.
Naveen,
Oh,
one request.
yes,
First, kindly give them about this particular environment. Then you
okay,
start, right?
Okay.
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 So actually, this is the software called Jupyter, Jupyter Notebook. So this Jupyter Notebook is used for running Python programs. It also used for data analysis. Okay, and then importing Python libraries and running here. So I have used a Python package called QSkit. Okay, I will show you the requirements. So these are the requirements we needed. Okay, the main thing we need here is IBM package called QSkit. So the version I am going to use here is 0.2.6.2. Okay, this is the version I am going to use. So there is also latest version available. Okay, so this is the user version I am using previously. Okay, so and then another requirement is we need MATLAB, Matplot library. Okay, and then we need a Python. So these are the prerequisites to install the software. Okay, I'm going to install those libraries in a Conda environment. Okay, I mean I'm using Miniconda. So Miniconda is used to create some virtual Python environment. Okay, so in those environment, I am going to install those packages: Matplot library, QSkit 0.26.2, and then Python. There I'm going to use QSkit IBM Quantum Simulator package to simulate quantum programs. Okay, this is the home page. So I have some basic programs here. Okay, I'm going to start with some few basic programs. It is a very simple Python program only. Okay, first I'm going to import the package called QSkit. So this is provided by IBM open source. Okay, it is available as a open source package. Okay, and then I'm going to import NumPy. So this is used for performing numerical operations. Okay, and then I'm going to import some supporting models like AER. Okay, and to create quantum circuit, I'm importing quantum circuit, and then to execute the quantum circuit, I'm using this package. Okay, and then I'm going to use quantum register to create qubits. Okay, and then to measure the state of the qubits, I'm going to use classical register. Okay, and then basic AER. This is provides a variety of simulators uh, like measuring state, measuring unitary matrix. Okay, and then so I'm going to use block sphere. Okay, block sphere is used to visualize the state of the qubit, and then histogram. So this will plot the histogram of the state, and then pi value, and then square root supporting functions. Okay, and quickly go through this program. Okay, I don't want to take much time. Okay, so I'm going to run this code. Okay, it has been imported. So I'm going to go through the version. So actually it shows the what are the versions I have used. I am using the Qskate version 0.26.2. So to ensure what version I am using, and then I have the backends function. This backends function gives the simulators which are developed in C++. So for example, it has the list of simulators. AR simulator, state vector to simulate the states, to simulate the unitary matrix, and then basic AR dot backends. So this is provide some three basic simulator to run quantum circuits or simulate quantum computer. So these are developed in Python code. Okay, I'm going to run the remaining code. Okay, so the first line I'm going to use is CR equal to classical register. Okay, the main use of classical register is to measure the result of the qubit. Okay, so whenever a qubit goes into the superposition, we cannot measure that value whenever it is in superposition state. We need to use a classical register to measure the state of the final result after superposition to the final state. Okay, for measurement purpose, I am using the classical register. Okay, and then I'm going to have another register called quantum register. Okay, the main purpose is to so the meaning I told. So the number one mentions that I am going to create a one classical register. The number first parameter indicates that I am going to create the one quantum register. So the name is CR and QR. So I'm going to create a quantum circuit. So the quantum circuit is made up of quantum registers and classical registers. So this is for storing the qubits. Okay, and then classical register is for measuring the state, final state. Okay, so that is the basic of this program. Okay, I'm going to run it and then simulate now. Okay, you can see there are two lines there, QR and then CR. This is the quantum register and then classical register. Okay, so the same program I have in another tab also. Okay, so in this tab I'm going to import the same thing, but now I'm going to create one quantum register. Okay, I'm going to integrate that quantum register into a quantum circuit called QCX. Okay, so now this is the main part. Okay, where I am going to apply poly X gate here. So poly X gate, it is like a classical NOT gate. It flips the initial state 0 to 1. Okay, that is the main use of poly X gate. Okay, so I'm going to draw this circuit using matplotlib library, that is MPL. Okay, so I have a quantum circuit with one quantum resistor. Okay, with a poly X gate applied. So I'm going to use a quantum simulator to run this quantum circuit. So the quantum simulator is given by the get backend function. Okay, so I'm going to execute the same quantum circuit and then get the result using result function. So I'm going to get the state vector using get state vector function. That result will be stored as a dictionary in the result variable. So finally that result will be shown here. So I am also plotting the blood sphere. So the blood sphere will be plotted here. So the initial state will be 0 always. So whenever you apply to the poly X gate, it will be flipped to 1. So next, I'm showing the unitary simulator value. So I'm going to run the same circuit using unitary simulator. So this will give the result. So whenever you give the input 0, the output will be 1. Whenever you give the initial state as 1, the output state will be 0. Okay, so again I'm going to get the unitary. Sorry, I'm going to run the same thing, another simulator called QASM simulator. So this simulator simulates the actual quantum computer. So we are going to run this circuit 1000 times using a execute method. So using the actual quantum computer simulator called QASM simulator. So with a sort of 1000 times, okay, this circuit will be executed. So each time when you execute the circuit, the initial state will be 0 only. So finally it will be become 1. So you will get the result 1000 times. So I'm going to put in the histogram. So you will get 1000 times there. So there are many other ways to create the same quantum circuit using with the barriers, vertical barriers, and so on. So and then another thing is called a C naught gate. Okay, actually C naught is a control gate. So control gate meaning is, okay, so whenever the input is 1, the one the gate will be executed. So actually whenever the input is 1 only, the connected gate will be executed. That is the C naught gate. Okay. Okay, for example, if the input is 0 and 1, okay, so the 0 will be flipped to 1 here. So now the 1 will be passed to this C naught gate. Okay, and then this gate will be executed. So this whenever one is passed to this control gate, this gate will be executed. If it 0 is passed, this gate won't get executed. So since we are passing 1 using the poly X gate, this gate will be executed. So the final output will be 0 and 0. So that is the result here. Okay, whenever I pass 1 and 0, so it will be flipped now. So it will become 0. So the control gate has the value 0 now, hence this gate does not execute. So the final output will be 0 and 0. So that is the output shown here. So in the state. So and then talking about Hadamard gate. So I'm going to create a quantum circuit with a Hadamard gate h of 0. So 0 means it is the index, it is not the count or initial state value. So it mentions the index. So it is like a array. For example, I'm going to create one QR register, quantum register, and then one CR, classical register. So the name of the circuit is QC. So I got one quantum register, one classical register for measuring, quantum register for storing the qubits, and then QC for the name of the circuit. So I'm applying the Hadamard gate at the 0th index. So the index 0 tells first qubit. Okay, it is the first qubit. Actually, I have only one quantum register there. So that is the one and only qubit. That is the first qubit. So finally, I'm drawing the circuit using MPL. That is Matplotlib library. Okay, I got a quantum circuit with one Hadamard gate with a classical register to measure the result. Okay, next I am going to use a state vector simulator to execute the circuit QC Hadamard gate. Okay, and then printing the result now. So I got two probabilities here. Okay, this probability is nothing but that 1 by root 2. So that is 0.707 probability. So it takes 0.707, I mean 1 by root 2. So when you square it, you will get the value 1 by 2. So the probability of going to the state 0 is 1 by 2, and then state 1 is also 1 by 2. So 50% is probability for 1, and then 50% is probability for 0. So this is called the Bell state condition. So that is called Hadamard gate. So Hadamard gate those puts the qubit in superposition state. Okay, I'm going to run the circuit 1000 times again. Okay, you can see that 0 is came 0.481, I mean sorry, 481 times. Okay, and the 1 comes 519 times. So it gives a nearly equal number of times the probability for going to state 0 and then 1. So nearly equal number of times using the Hadamard gate. Okay, so this is the three basic programs for creating quantum circuits for C0 gate, poly-X gate, okay, and then a Hadamard gate. Okay, now I'm going to pass the session back to ma'am. Okay, thank you, ma'am.
Uh, uh, Naveen, please wait.
Okay.
Okay. So hope participants hope you have some idea about implementing these gates using QSkit by Python Jupyter notebook. If you have, I will give you 5 to 7 minutes time for asking any questions.
Okay, ma'am. We'll start next session within 10 minutes, ma'am.
Yes.
Okay, ma'am. Well, 10 minutes break now.
Yeah.
Participant, be online. Be online. The next session will start after 10 minutes.
Sir, where can we give the attendance?
Ma'am, attendance will be automatically generated. You will
Okay,
receive.
sir. Thank you.
Okay.
Okay, sir.
Okay, sir.
Naveen, please wait. We'll clarify after break. Okay.
Oh, okay, ma'am.
Okay, ma'am. Okay.
Ma'am, can we have these programs?
Ma'am, everything we will share you through your mail, ma'am. Okay. We'll collect it from the resource person and we'll share you later.
Sir, along with the YouTube links also, you can please share, sir.
Yeah, sure.
Thank you, sir.
Participants, have you came back?
Yes, ma'am.
Yes, ma'am.
Yeah. So now I open the session for clarifying your doubts in writing simple programs using QScript. If you have any clarifications to be made, you can ask us.
Ma'am, good evening.
Yes, good evening.
Ma'am, what will be the time taken to execute this program when compared to the classical computer and QSET computer
No,
program?
actually, yeah, it's a good question. Actually, right, all these things are just simulations. What we are looking into the Python environment using Jupyter notebook, we're just simulating the concepts for having the better understanding. But if you are doing the real computation in the quantum computers, so it will be even it will not for huge computation itself. It is taking some, I mean, very minute time it is taking for execution. Whatever we are
Ma'am,
doing here is a
usually we take
simulation.
now from milliseconds. Now we are computing in nanoseconds. So what
Not
about this qubit simulation?
more than that. I mean, it is still reduced. It's still reduced
No,
based on
suppose now we are computing and we want to find the comparative results. Then how the simulation results will help us to compare.
No, actually, if you want to do, if you go and see the IBM utility package for doing the quantum computation, for learners and for teaching perspective, they are providing us a free service. So even that is a simulation. If you want to do the exact computation, it is a payable version actually. So actual computation is a commercial one, but it will take only very less time for computing the very challenging problems. Now, see, normally we are.
Can you just tell me what type of data set we can give, and how can we compare these both computations while using this qubit and then using the normal bits?
See, when you take problems that you want to apply it in the quantum computer, if you want to use it in the quantum computer, that problem cannot be handled by the classical computer. Okay, for example, suppose if I wanted to compute, I mean, we are using the machine learning aspects, right? So nowadays we are going into machine learning and deep learning. Example I am telling, machine learning and deep learning algorithms, which are very much useful for getting the results and predicting the various possible outcomes, right? Even that, when the size, there are a lot of challenges in handling data set when you apply machine learning algorithms. Okay, so we come across some underfitting and overfitting problems, and because of that, we couldn't be able to identify the proper results. And whatever results we are getting may not be exactly what is being expected. All these issues are we are facing when we go for the data sets. Suppose if you take the data sets in the healthcare domain itself. So when we use the quantum principles for solving certain type of problems, so we have two major concepts like superposition and entanglement, right? So
Can we use this in fuzzy logic also? Because of this zeros and ones, we have an intermediate state. Now then, how can we compare this fuzzy logic and this qubit? Because even fuzzy logic, when you have zeros and ones, we are not able to predict. That's why we got into this fuzzy logic.
Yeah. Fuzzy logic is also doing what it does. It is again classical computing only.
Yeah, but still, since we are not able to decide between 0 and 1, we have another states
Yeah,
from
it is an
between 0 to 1.
undecidable, right? Whatever you are telling is either whether it is 0 or 1 is very fuzzy. Using certain algorithms, we are come to a conclusion that this would be the probability that we can end up. Okay, so that is fuzzy. But when you go for the quantum, you have intermediate stages, like when it becomes 0 to 1, what are the probabilities that in how many times the 0 is coming as the probability and 1 is coming as the probability. That is not being covered in fuzzy.
With the number of iterations, can we guess the outcome?
Only you can guess, but here the particle level it is going and working.
Yes, ma'am. For example, as you said, when you flip a coin, so the transition between the start of the toss and then ending up, you have the transitions. The number of transitions, can we guess the outcome?
No, you cannot guess actually. What it does is,
or you can decide the outcome. If not guess, at least you can decide the outcome.
Because quantum is being useful for undecidable problem exclusively and hard problems. We are studying, right, in data analysis, right? So hard problems, soft problems. In hard problem and for you can very well undecidable and hard problems, you can very well use quantum. So even in classical computing, you may use hard problems. For example, if you we are solving the 8 queens or n queens problem, right, using classical computing. The time taken for computing the n queens problem will be whatever we feel is nowadays. If you use supercomputer, it may be less. But even more less than that of time, if you try it out in the quantum, it will be 1/100th of time it is less. 100
Thank
times
you.
better. Yeah. Thank you.
Hello, ma'am.
Hello.
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 Ma'am.
Yeah.
Yes, ma'am.
Yes, ma'am.
Can you tell me what is the exact difference between Qiskit and Q sharp?
Qiskit and Q-Share is actually both are using in the same. See, both the kit you can simulate and you can see what would be the output. See, like in Python we are using scikit. See, in Python we are using scikit, Kaggle, like that various environments we are using, right? So like that
Yes,
you can use
2DK.
any, like that you can use any simulators for doing. There is no much differences.
Okay, and when I want to store a quantum image, so which environment is better?
Quantum image, I think Qiskit is better.
Okay. Yes, ma'am. Thank you.
Yeah, thank you.
Hello, ma'am.
Hello.
Ma'am, actually, now I can understand the difference of classical and quantum.
Yeah.
But whatever we are discussing is how the quantum computing, I mean, working or what we are actually going to discuss now. How we are going to.
Yeah. Have you gone through the schedule which is given by this FDP, ma?
Yes, ma'am. Actually, concepts they have given, basics they say.
Yeah. Actually, yeah. They're starting from this basics. They are moving slowly towards the gate execution. Even the very basic gate programs today it is being covered. So the circuit design using the quantum gates will be done in a detailed way tomorrow. Then they slowly take up the algorithms, Shor's algorithm and other algorithm, which is very much been effective algorithms for doing solving various problems. That is also been covered in the FDP. It is
Okay,
actually,
ma'am.
yeah.
Thank you. How the
Been
quantum will be working
yeah,
that we will study, right, ma'am?
Pardon, ma?
How the quantum computing will be working, or how the quantum computing have been constructed,
Yeah.
like that.
You will get a complete idea. So
Okay,
in the
madam.
next step, if you want to do any research or if you want to give solution to some problem, definitely you can try out.
Okay, ma'am.
Yeah.
Thank
Thank you. Thank you. So hope we had seen the nodes and other things in the execution itself. When you find time, see the examples here. And the other part of the session would be the global perspective of quantum computing. See, so we have covered, right? It is I mean, it's just an idea how the world is moving towards the quantum. Okay, so it is actually, we discussed like it is useful for solving the intractable problems, and it's been applied in the fields like medicine, material science, medicine, exclusively in the medicine, right? So when they produces the drugs, so it is like, I mean, different molecule, based on the combination of different molecules and the interactions, the new drug will be produced. So in that way, definitely this quantum will have a revolution. So when they try out with different combination of molecules, they will come up with the different drug discovery, and which is very much helpful for the medicine field. Okay, so again, then material science also, they, when they go for manufacturing certain materials, and they are try out with different combinations, and they are having the different materials to be introduced to the world with a very faster and in a very efficient way. So again, I told you, artificial intelligence, again, if it has been combined with the quantum concepts, definitely the efficiency and accuracy will be high. Finance, so we all heard about the stocks and trading sectors. So every day it's been changing, and it may do predictions like what is the possibility of the particular stock would get raised or coming down, or what would be for the past 1 year, what would be the status, what would be the when it compares to other stocks, what would be the comparison, all different types of combinations that can be tried out here, that can also be passed, that can create the evolution in the field of finance. So again, it's not evolved completely, it's all being tried out, and scientists are being working even now. There are countries which are very keen on leading the research and leading the quantum business. The countries and regions who are doing the highest business are North America. If you take IBM, Google, and Microsoft, INOC, and Riget, they are invested. And Canada, again, two more companies have given their interest. Europe, if you see, like UK and the EU are having shown their interest for doing this quantum research and quantum business. And Asia, if you see, right, the Chinese people, they have, and government itself, they shown interest, and for investing much in quantum domain. And Japan and South Korea and Singapore, again, they are showing pretty much of interest in doing the work and research work, as well as the commercial work in the field of quantum. Okay, so this give you the some I mean, quantum race, who are the people who are involving, how the governments are leading into quantum computing. So as usual, we have the USA, China, and EU are taking the highest run so far in the field of quantum. Then if you see the focused area are, so majorly if people who are who wants to do I mean, so I think nowadays there are people, plenty of researchers were going on, and there are people who are doing research also. It's better to go for work on quantum algorithms, quantum software. Okay, so you can suggest your own small upgradation, even if it is a small contribution. So it will be having the better recognition in the world. Okay, so don't be have always see people nowadays, the machine learning and deep learning, Gen AI is little bit there are scope. So machine learning and deep learning already exhausted. If you combine along with the machine AI, if you combine the quantum logics, then yours will be very good research. I mean, project. So the algorithm, Shor's algorithm for factoring the prime numbers will be covered in the session, upcoming sessions. One day it is specifically it is being given. Definitely the hands-on will also be given, I hope. See to that these are the areas where you can show interest in doing the research. And the industries which are transforming from this I mean, quantum would be drug industry, I mean, drug discovery, new drugs can be discovered, and material science and finance, which is having the tremendous change in the investment portfolios, and artificial intelligence. Again, cryptography will have a wonderful future for this. Then the road ahead would be, so building stable and scalable quantum computers are, again, it is being worked on, and developing quantum workspace, and there is always a need for skilled researchers and engineers and developers for the quantum field, and ethical considerations should be covered, and international collaboration is also having the wider scope. Okay, so future would be like rapidly evolving field. Definitely, it changes our world. Then there is a global collaboration for investment, and definitely there are plenty of challenges and opportunities will be there. So when we work on this particular field, okay. So those who are so we have a small quiz again. When two or more qubits are linked together in special way, then it is called as entangled, right? So next question, can anyone try? Which of the following is a key implication of quantum entanglement?
Teleportation of matter.
Yeah, very good. See, what is the answer?
See, second quantum cryptography.
Yeah.
Okay.
Then what is the teleportation of matter?
Yeah. In teleportation also entanglement is useful, but key in the main application is cryptography.
Okay.
Yeah. What happens when you measure a qubit in superposition?
It remains in superposition.
Is it? What would you do with a gate circuit then? It collapses into definite state, right? So if it is in superposition, we are in position to find out whether it's 0 or 1. Okay. So then, which of the following is not a physical realization of qubit? Physical realization, not a physical realization.
Photons.
No, it's a radio waves. Photons are the main realization of qubits. Then, what type of matrix is used? Unitary matrix,
Unitary matrix.
which helps us to represent the complex numbers. Okay, so at last we are coming to an end, right? So definitely, I hope this is an eye opener for you to attending this particular FDP on quantum. So I'll give you some 5 more minutes to clarify your final doubts. We have started with by comparing the classical with the quantum and need for quantum. Then we slowly moved on to quantum concepts. Then from the concepts, we moved on to the quantum gates. Then we have seen various examples and the practical implementations too. In between, we had seen, for the better understanding, we had seen the visual video representation of the concepts. Then we had seen quizzes, and then we have seen the global perspective of quantum, and now we are coming to an end. Thank you all for your wonderful cooperation and the interaction with me, and definitely in future, if you are willing to work with us, we welcome you.
Ma'am, like in classical networks, we have the switches, routers, and the repeaters, which we'll use for the other purpose. Like that, in quantum networks also, we have the switches, routers, and the repeaters. And what are those names? Can you?
No, actually, here they renamed the gate itself as a quantum gates, right? So what you have to think is like the basic infrastructure for network communication would be same. Only the computation part would be different.
Okay.
Yeah.
The functionality is also same, ma'am?
Yeah. Network side is completely different. Only the processing side, it is playing the vital role.
Okay.
Yeah.
Thank you, ma'am. Thank you for giving me this
Good evening, madam.
very good informative session.
Thank you, ma'am. Thank you so much.
Good evening, madam. This is Varna. I
Yeah.
just want to know regarding if anyone wants to do with the security part. So, what should be the basic information the person has to know regarding the security algorithms?
Yeah, if you know all basic cryptography algorithms, that's good. Otherwise, you learn basic cryptographic algorithms first. Then you just see what is the possibility of, I mean, writing those algorithms in the quantum way.
Okay, ma'am.
Yeah.
Okay, thank you.
For that, you have to thoroughly understood the cons. For example, if you take RSA or Diffie-Hellman, you
Yes.
should know how it is being operating. Then, in the similar way, if you want to same algorithm, if you would like to implement in quantum, what are the necessity and needs that are required from quantum side, and that analysis, if you made, it is easy only. You can do the simulations.
Surely, ma'am.
Yeah.
Thank you, ma'am.
Yeah. Thank you.
Participant, any more clarification?
Ma'am, can we combine classical networks with the quantum networks in terms of speed and the efficiency?
No, what you have to even through simulations you can compare classical and quantum, but you cannot combine. See, certain problems cannot be solved immediately by the classical way because it takes years together to solve problems. In that case, you cannot able to compare at all the outcomes. But some small problems, if you would like to compare, it's possible.
Okay.
Yeah.
Participants?
Yes, sir.
Any more question?
No, sir. Thank you, sir. Thank you, ma'am. Thank you so much.
Yeah, thank you.
Thank you,
Ma'am,
ma'am.
Thank you.
ma'am, thank you so much for your wonderful presentation.
Yeah, thank you, Pa.
Thank
Thank you, ma'am.
Thank you all for your very cooperative learning, and it's give me a very greater opportunity. At this juncture, I would like to thank Gopi and his team for putting in wonderful effort for getting this FDP from Atal, and it's a great community service too for enabling you all with the concept of quantum. The great thanks to the team. Thank you.
Thank you, ma'am.
Thank you, Pa.